Hey mechanics friends, nothing says summer but grilling, and who doesn't like grilling? And so I thought for pressure vessel day we would talk about grilling a little bit, because we'll see that usually a day out at the grill will involve a few pressure vessels. So to recap our learning objectives for today, we're going to determine some equations for longitudinal stress and hoop stress for pressure vessels, and then we're going to apply those equations to solve some engineering problems. Alright, so I said that grilling usually has a couple pressure vessels involved. So when you're grilling, who doesn't enjoy their favorite beverage? So my favorite beverage is Dr. B, Dr. Battistini, but whatever, who cares, whatever you want to drink, that's fine, but I'm sure you're going to experience a pressure vessel. We also have our grill, right? Our grill, we have the pressure vessel down there holding our propane that's going to keep our grill lit. It's also summertime, so maybe you're going to have a little bit of a celebration. So to celebrate, what else do we do but we blow up some balloons, right? So I'm going to grab a special balloon and blow it up here in a second for you. Alright, this is my special pressure vessel balloon. Basically, it has some markings on it that's getting all over my hands now. But when you take a balloon, right, we blow it up, and what happens to it? Well, we know it expands, right? And how would you think that it expands? Does it expand, uniformly? Does it expand more in one direction than the other? Yeah, I mean, it depends maybe on the balloon shape. So I'm going to give this balloon a try. So you can see I have what's the start of a little element, so our stress block element. I'm going to keep inflating the balloon. Alright, so we get something that looks like this, right? So this is our stress block element on the balloon. We see that it started very small, but for the balloon, it mostly expanded uniformly in both directions. It's a little bit of an oblong shape, so maybe it's not quite perfect. But we do recognize that the balloon has stretched in 2 dimensions, making this a case of plane stress. Alright, well, I could go on for ages about this, but I'd probably be just a bunch of hot air. I do want to take you, I do want to start getting grilling. So I got some nice hot dogs here. So I'm going to throw them on the grill, and I'll catch you in a little bit after you take a few notes. Hopefully with that balloon example, we are well on our way to understanding the stresses that are acting on an element inside a pressure vessel. So the balloon is maybe more of a spherical pressure vessel as opposed to this compressed air container, which would be more of a cylindrical pressure vessel. So I want to investigate what's happening at point A. And so like the balloon, we are expecting it to stretch, and we're going to expect it to stretch in both the circumferential direction around the circle of the cylinder, as well as in the longitudinal direction along the length of that cylinder. So we see that as we pressurize the tank, the wall should expand and we should experience some sort of sigma 1. We call this the hoop stress or the circumferential stress. So this is the stress that's acting around the circumference of the circle. We also get a longitudinal stress. So we have to imagine those end caps are being pressurized and stretching the entire cylinder. That is called the longitudinal stress, and we'll call that sigma 2, and I've labeled it here in green. We can't forget that the air pressure itself creates a compressive stress acting on the inside face of this element at point A. So I'll draw that here in red. And again, this is going to be a compression strength because we have the gas or liquid, or it can even be a solid on the inside, pressurized, and that pressure is pushing on the inside face of that element. Now the outside face is exposed to the atmosphere, and so it has basically no pressure acting on it. So we have a discrepancy from a statics point that sigma 3 is not balanced. So what do? In reality, sigma 3 will be dissipated by shear through the thickness of the wall. But when we have a very small thickness, we can take advantage of what's called the thin-walled approximation. In this type of an analysis, we assume that sigma 3 is roughly equal to 0. And this will be true because relative to sigma 1 and sigma 2, sigma 3 is usually a very small value. So if that's the case, we can ignore sigma 3 in our analysis and just look at sigma 1 and sigma 2 as applied to the element. Now, when can we take advantage of thin-walled approximation? We can do this whenever the inner radius over the thickness is greater than or equal to 10. So how do we come to this number? Well, we find that if you use the thin-walled approximation with a value of r inner over t equal to 10, that will result in calculated stresses that are within 4% of the real stresses obtained from a thick-walled analysis. So a full analysis of the structure with the pressure on the inside, the thin-walled approximation will be within 4% if r over t is equal to 10. And as r over t goes up, that error will be further reduced. And usually for a lot of our pressure vessels, this value is going to be much greater than 10. All right, before we move on to talk about and go through one of these analyses, I want to ask you the question that without having a mathematical formula, do you have a physical feel as to which of these stresses will be higher? Will the hoop stress, sigma 1, be higher? Or do you think sigma 2, the longitudinal stress, will be higher? Or do you think they're going to be the same? So go ahead and think about that as you queue up the next video. In that video, we'll see a model of a cylindrical pressure vessel that'll help us remember the relationship between sigma 1 and sigma 2.